We expect James Webb to make great discoveries. We expect that in the vastness of space, humanity has always been curious about the mysteries of the universe. Since it began its mission in 2021, the James Webb Space Telescope has been quietly looking deep into space, taking pictures that are changing how we see our place in the cosmos. Recently, in a jaw-dropping discovery, Webb has found something incredible. This strange finding breaks the laws of physics and puzzles our understanding of reality, leaving scientists feeling uneasy. Are we alone in the universe, or are there hidden forces waiting to be uncovered? Join us as we unravel the recent discovery made by the James Webb Space Telescope. Dark matter is like a hidden secret in the universe. It's this mysterious stuff that we can't see directly, but we know it's there because of how it pulls things with its gravity. It's kind of like a cosmic ghost hanging around and affecting everything around it. Scientists think it makes up a huge chunk of the universe, around 25%, which is a big deal considering we can't even see it. This whole dark matter thing has been puzzling scientists for a long time, ever since this guy named Fritz Zwicky first suggested its existence back in 1933. It's weird because, even though it's everywhere, we can't catch it in the act. It's like trying to catch a shadow. For a while, scientists thought the universe was slowing down, but then along came NASA's Hubble telescope, peering deep into space and discovering something mind-blowing. The universe is speeding up. This shook things up big time. It's like finding out your car is accelerating when you thought it was slowing down. About 95% of the universe is made up of this invisible duo called dark matter and dark energy. They're like the backstage crew of the universe, doing all the heavy lifting while the stars take the spotlight. Now we've got this fancy new gadget called the James Webb Space Telescope, JWST, and it's like the superhero of space gadgets. It's got this massive mirror and can zoom in on stuff far away. For scientists studying dark matter, this is like hitting the jackpot at the cosmic casino. The JWST can do this cool trick called gravitational lensing. Imagine you're looking at a distant galaxy, but there's a closer galaxy in between, bending the light from the distant one. By measuring how much the light gets bent, scientists can figure out how much dark matter is hanging around the closer galaxy. Now, some smart folks in Italy are using the JWST to study galaxies from way back, like 13 billion years ago. They're also using super fancy computer simulations to understand how the first galaxies formed. There are different ideas about what dark matter is made up of. Most folks think it's this cold stuff that only interacts with gravity, but some researchers think it could be warmer with tiny bits moving around faster. It's like the difference between ice cubes and hot cocoa. Dr. Umberto Maio, a researcher at the Italian National Institute of Astrophysics, explains that the recent discoveries made by the James Webb Space Telescope regarding galaxies formed in the first billion years after the Big Bang are invaluable for understanding the early universe. In a study just published in Astronomy and Astrophysics, Dr. Maio and his team revealed that these discoveries shed light on the nature of dark matter, the mysterious substance that makes up most of the matter in the universe. Dark matter consists of particles that are either cold or slightly warm, with masses greater than 2 keV. By analyzing data from the JWST and running advanced simulations, the researchers were able to rule out certain dark matter models with particle masses equal to or less than this limit. This study stands out because it utilizes data from much earlier cosmic times than previous research, providing new insights into the properties of matter. Dr. Maio explains that the structure of the universe, particularly during the era when the first stars and galaxies formed, is heavily influenced by the mass of dark matter particles. The team found that different dark matter models lead to variations in cosmological phenomena such as star formation rates, ultraviolet luminosities, and molecular abundances. By leveraging the latest JWST data, researchers can compare these variations and refine our understanding of dark matter. This research marks a significant milestone in our quest to understand the early universe. By observing the most distant galaxies, scientists gain valuable insights into their composition and evolution. Dr. Mayo believes that as more data becomes available, particularly regarding smaller and younger galaxies, we will uncover additional clues about early stellar formation and galaxy properties. The discovery of these early galaxies is remarkable because it demonstrates that complex structures can form rapidly in the cosmic timescale. This discovery paves the way for future studies to delve deeper into the nature of matter and the formation of galaxies. As technology advances and more powerful telescopes become available, we can anticipate even more exciting discoveries that will further expand our understanding of the universe's origins. Besides the ongoing investigation into dark matter's nature, another theory put forward by an astrophysicist at Oxford University offers a promising solution to a long-standing puzzle. Jamie Farnes suggests that dark matter and dark energy might coexist as a dark fluid composed of negative masses. This peculiar substance possesses negative gravity, which repels objects instead of attracting them. Farnes's theory, outlined in a paper published in Astronomy and Astrophysics, seeks to shed light on some of the universe's enigmatic characteristics, such as the rapid rotation of galaxies without tearing themselves apart, thanks to the protective embrace of dark matter halos. According to this theory, the presence of a negative mass dark fluid could catalyze the formation of these protective halos. However, a challenge arises if dark energy diminishes in density over time, contrary to observations indicating its relative constancy. To tackle this conundrum, Farnes proposes a theory of matter creation. This hypothesis suggests a continuous generation of new substances to replenish disappearing negative matter. Farnes offers a captivating analogy to illustrate his idea. He envisions spacetime as a bowl of popcorn with negative masses popping into existence, akin to kernels turning into fluffy popcorn. While Farnes's dark fluid theory presents a captivating narrative, it remains just that, a theory grounded in mathematical models and computer simulations. Farnes himself remains cautious, refraining from asserting it as a definitive explanation. Other scientists rightly approach it with a healthy dose of skepticism. Although the theory appears to elucidate some aspects of the universe's behavior, the pivotal question lingers. Can it satisfactorily address all other observed phenomena? Geraint Lewis, a professor of astrophysics at the University of Sydney, warns that before we jump to conclusions about a new theory, there's a lot of groundwork to cover. He points out that the big challenge lies in understanding something called negative mass and how it fits into what we already know about the universe. Lewis emphasizes that while we can write fancy equations for different phenomena, it's only by carefully observing and testing these ideas that we can truly understand if they're real or not. To tackle these questions, organizations like CERN are conducting experiments exploring the possibility of negative masses, just like those proposed by Farnes. The Square Kilometre Array, the world's largest radio telescope currently in development, is another example. Lewis sees great potential in such endeavors, believing that by pushing the boundaries of fundamental physics, we can ultimately improve our everyday lives. But that's not all. Scientists have another intriguing argument. When we look out into the visible universe, which includes Earth, the Sun, stars, and galaxies, we see stuff made up of protons, neutrons, and electrons, the building blocks of atoms. However, a mind-blowing revelation from the 20th century tells us that ordinary matter, also known as baryonic matter, makes up less than 5% of the universe's mass. The rest seems to be made up of something called dark matter and another mysterious force known as dark energy, which seems to push things away from each other, countering gravity. This realization opens up a whole new realm of questions and possibilities in our quest to understand the cosmos. Most scientists are still trying to directly see dark matter. This stuff doesn't interact with regular matter and is invisible to light and other kinds of radiation, so with our current tools, we can't spot it. but we think it's out there because it seems to affect how galaxies and groups of galaxies move because of its gravity. Let's think about a spinning spiral galaxy. Stars near the center, where most of the galaxy's matter is, should move faster than those farther out. But when we look, they all move at about the same speed. This is odd. It starts to make sense if we imagine there's this invisible mass of dark matter around the galaxy, tugging on the stars with its gravity. Some scientists think we might need to rethink how gravity works to fully understand this. Now onto dark energy, which is even weirder. When scientists first found it, they were surprised. They thought gravity would slow down the universe's expansion over time, but when they measured it, they found it was speeding up. It's like throwing keys up in the air and expecting them to fall back down, but instead, they shoot up toward the ceiling. Now, scientists think this speeding up is because of something called quantum fluctuations in space. These fluctuations create a kind of push, making the universe expand faster and faster as time goes on. Some think this fits with an idea Albert Einstein had called the cosmological constant. He thought this constant could act like a repulsive force, pushing against gravity and keeping the universe from collapsing. But he ditched the idea when he realized the universe was expanding. However, now with dark energy, scientists are revisiting this idea, trying to understand why this mysterious force exists and what it means for the fate of the universe. In Berlin in 1915, amidst the turmoil of World War I, Albert Einstein introduced a groundbreaking theory of gravity known as general relativity that replaced Isaac Newton's long-standing ideas. By 1916, Einstein applied this new theory to the most massive object he could think of, the universe itself. His calculations led to a remarkable conclusion. The universe couldn't remain still. It had to be either expanding or contracting. This idea remained theoretical until 1929, when American astronomer Edwin Hubble made a revolutionary observation. He noticed that galaxies were drifting apart as if propelled by a colossal explosion. This discovery was later understood as evidence of the Big Bang, a moment when the universe began expanding. Essentially, Hubble observed that the space between galaxies was growing larger, implying that the universe itself was expanding. Einstein's theory accommodates various models of the universe. One possibility is that the universe stretches infinitely with no boundaries. Another possibility is that it curves back on itself like the surface of a higher dimensional sphere, creating a finite but unbounded universe. In this latter scenario, if we had powerful enough telescopes, we could theoretically see the same galaxies on opposite sides of the universe. Some scientists argue that the universe does have an edge, not in a physical sense, but in terms of time and visibility. They point out that the universe began with the Big Bang approximately 13.82 billion years ago. Consequently, the farthest objects we can observe are those whose light has had enough time to reach us, 13.82 billion years. This distance forms what we call the observable universe, a sphere with Earth at its center. Despite this, the universe's expansion has stretched this sphere to a diameter of about 92 billion light-years. The observable universe is surrounded by what we refer to as the cosmic horizon, similar to the horizon we see at sea. Just as there is more ocean beyond the sea horizon, we know there are countless galaxies beyond the cosmic horizon whose light hasn't reached us yet. One of the pressing questions in modern astronomy is whether the James Webb Space Telescope, JWST, can see the edge of the universe. The JWST, with its advanced technology, is designed to look deeper into space and further back in time than any previous telescope. It can detect the faintest and oldest light in the universe, potentially observing objects that existed just a few 100 million years after the Big Bang. While it won't be able to see the absolute edge of the universe, since the edge is continuously moving as the universe expands, it will help us understand more about the early universe's formation and evolution. When thinking about spending $10 billion on a space telescope, it's natural to ask if it can truly see that far into space. The James Webb Space Telescope is 100 times more powerful than the well-known Hubble Space Telescope. This advanced telescope can capture extremely faint infrared light from the very first galaxies in the universe. It's also designed to study planets orbiting other stars in our galaxy and check their atmospheres for signs of life. However, there's still uncertainty about what scientists will discover when they point the telescope towards the edge of the universe. To understand this, we need to know about the observable universe and the unobservable universe. The observable universe includes everything we can see if we can detect all types of radiation. But there's a limit to what we can observe. The farthest light we can see comes from the cosmic microwave background, which appeared about 13.8 billion years ago. At that time, the universe was like a thick fog, making it opaque. Some scientists think that gravitational waves and neutrinos, which are tiny particles, might come from even further away. However, we can't confirm this yet, because we don't have the necessary technology. Cosmologists who study the universe say that the observable universe is just a small part of a much larger reality. One of the farthest galaxies discovered by scientists is called Abell 2744Y1. This galaxy is notable for several reasons. It is so far away that its light takes 13 billion years to reach us. Considering the universe is estimated to be 13.8 billion years old, this means we are seeing Abell 2744Y1 as it was when the universe was still very young, about 650 million years old. This happens with all distant objects in space because the light from these faraway objects has traveled such a long distance to get to us. The discovery of Abell 2744Y1 involved 3 different telescopes: Spitzer, Chandra, and Hubble. Each of these telescopes works with different parts of the electromagnetic spectrum. Spitzer uses infrared light, Hubble uses visible and near-infrared light, and Chandra collects data using X-rays. By combining the data from all 3 telescopes, scientists were able to study galaxies much farther than any single telescope could have managed on its own. Spanish astronomers from the Instituto de Astrofísica de Canarias, IAC, and La Laguna University first used the Hubble Space Telescope to detect the galaxy. Next, they used Spitzer's instruments to measure the distance between the galaxy and Earth. Spitzer also helped estimate the number of stars in the galaxy. In addition to imaging Abell 2744Y1, the scientists used a technique called gravitational lensing. This concept is similar to how a magnifying glass bends light. Closer galaxies act like a magnifying glass, bringing the images of distant galaxies into focus. Albert Einstein's general theory of relativity predicted this natural telescope effect, allowing us to see the most distant objects in the universe. Gravitational lensing occurs because the massive gravitational field of a closer galaxy bends the light from a more distant galaxy, magnifying it and making it visible to our telescopes. The galaxy Abell 2744Y1 might be small, but it's still fascinating. Measuring about 2,300 light-years across, it is nearly 50 times smaller than our Milky Way, which spans around 100,000 light-years. Despite its small size, Abell 2744Y1 excels in producing new stars. It creates stars at a rate 10 times faster than the Milky Way, a characteristic feature of young galaxies in the early universe. Astronomers use a term called redshift to describe how far light from a galaxy has traveled and how much it has shifted toward the red end of the spectrum. This shift happens because the universe is expanding. Abell 2744Y1 has a redshift of 8, which means its light has been traveling for a very long time, almost to the point of the Big Bang. Before discovering Abell 2744Y1, the most distant known galaxy had a redshift of more than 7. From exploring the farthest galaxy ever captured in an image, we now turn our attention to another distant marvel of the universe. This time we're looking at a supernova, So, what is the most distant supernova ever discovered by astronomers? The record for the most distant supernova goes to one named DES 16C2mm. If you're curious about the name, it's because this supernova was found by the Dark Energy Survey, a scientific project aimed at understanding that mysterious force believed to be causing the accelerated expansion of the universe. Supernovae are some of the most powerful explosions ever observed. Imagine an atomic bomb, but with a blast that is incomparably more immense. These explosions mark the spectacular end of a star's life, its final dramatic act before it ceases to exist. The stars that end their lives in supernovae are typically at least 5 times bigger than our Sun. To better understand how these stars meet their explosive end, let's take a closer look at their life cycles. Stars are born from clouds of gas and dust in space. Over time, gravity pulls these clouds together, causing the material to collapse and form a star. In the core of this new star, nuclear fusion begins, generating the energy that makes the star shine. For most of a star's life, it remains stable, balancing the outward pressure from nuclear fusion in its core with the inward pull of gravity. However, this balance can't last forever. When a massive star exhausts the nuclear fuel in its core, it can no longer support itself against the pull of gravity. The core begins to collapse under its weight. As the core collapses, the outer layers of the star are still falling inward. This rapid collapse generates incredible heat and pressure. When the core can't be compressed any further, it rebounds, sending shock waves through the star. These shock waves cause the outer layers of the star to explode outward in a supernova. The energy released in a supernova is so immense that it can outshine an entire galaxy for a short time. This colossal explosion scatters the star's material into space, where it can eventually form new stars and planets. In this way, supernovae play a crucial role in the cosmic cycle of matter and energy. DES 16C2nm, the record-holding distant supernova, was identified by the Dark Energy Survey, which is specifically designed to explore the universe's accelerating expansion. This survey uses a powerful telescope to map a large portion of the sky, looking for evidence of dark energy, the mysterious force driving this acceleration. In the process, it also captures images of distant astronomical objects, including supernovae. The journey of scientists in identifying the supernova, known as DES 16C2nm, has been filled with numerous challenges. However, their efforts are expected to yield many significant rewards. This supernova, located at a vast distance from Earth, offers scientists a fresh perspective on the nature of a rare type of supernova known as a superluminous supernova, or SLSN. Superluminous supernovae are incredibly bright and powerful cosmic explosions. By studying DS 16C2nm, scientists can gather a wealth of information about these extraordinary events. One of the key aspects they examine is the ultraviolet light emitted from the supernova. This light holds valuable clues about the explosion. By analyzing it, scientists can determine how much matter was created during the explosion. This is crucial because it helps them understand the scale and intensity of the event. Additionally, the ultraviolet light can reveal the temperature at which the explosion occurred. Temperature plays a vital role in understanding the dynamics of these massive cosmic explosions. Knowing the temperature helps scientists piece together the conditions that led to the explosion and what drives such immense energy release. The study of DES 16C2nm is not just about understanding a single supernova. It opens up a new window into the broader phenomenon of superluminous supernova. These events are relatively rare, and every new piece of information helps scientists build a more comprehensive picture of how they occur. With each discovery, they move a step closer to unlocking the secrets of these powerful cosmic events. The discovery of DES 16C2nm has also spurred scientists to search for more distant supernovae. The excitement and insights gained from studying this supernova have motivated researchers to look even further into the cosmos. They hope to find more examples of superluminous supernovae, which will provide additional data and further enhance their understanding. Finding these distant supernovae is not an easy task. It requires advanced technology and sophisticated techniques. Telescopes and other instruments must be finely tuned to detect faint signals from such distant objects. But the potential rewards are immense. Each discovery adds another piece to the puzzle, helping scientists unravel the mysteries of the universe. Recently, astronomers have been puzzled by something called vacuum energy. This is the energy present even in the emptiest parts of space. When we measure this energy on a huge scale, like the size of the universe, and compare it to a tiny scale, like the smallest particles, we find a massive difference, 122 orders of magnitude. It's like comparing a grain of sand to Mount Everest. Some clever scientists have proposed a solution called the generalized holographic approach. They suggest that if we consider the tiny fluctuations or little ripples in the vacuum, we can bridge this huge gap. When we include these tiny ripples in our calculations, something amazing happens. It's like finding the missing piece of a puzzle. Suddenly, our universe starts to resemble a black hole, those mysterious cosmic whirlpools where gravity is so strong that not even light can escape. This theory becomes even more interesting with the recent findings from the James Webb Space Telescope. The telescope has detected 6 gigantic galaxies, each up to 10 times larger than our Milky Way, appearing just 500 million years after the Big Bang. According to the Big Bang model, galaxies of this size shouldn't exist so early because they require billions of years to form. These galaxies are not quasars, which means something else must be going on. Dr. Ivo Labbé from Swinburne University discovered these galaxies using images from the James Webb Space Telescope's near-infrared camera, released in July 2022. The extreme redshift of the light from these galaxies suggests they formed very quickly in the early universe. This rapid formation defies the common belief that galaxies start small and merge over long periods to become larger. Moreover, these galaxies contain much more mass than should have been available at that time, indicating they have gone through many cycles of star formation. All of these observations contradict current astronomical models and suggest that our universe might have been created by a gigantic black hole. The idea is that our universe could have evolved from a black hole in another universe, a concept dating back to Albert Einstein's theory of general relativity. According to this theory, massive objects like stars can warp space-time, creating gravity. Black holes, which form when massive stars collapse, are regions where gravity is so intense that even light cannot escape. Theoretical physicists like Nikodem Popławski from Indiana University have proposed that our Big Bang might have been the result of a massive star collapsing into a black hole in a parent universe. In this scenario, our universe could be inside a black hole in another, larger universe. Matter and energy pulled into a black hole might pop out on the other side in a different place, possibly in another universe. This exit point is called a white hole. Imagine a black hole and a white hole as two ends of a tunnel, called a wormhole, which acts like a shortcut through space and time. Popławski's intriguing idea suggests that when a massive star collapses and forms a black hole, a whole new universe could be born from the white hole at the other end of the wormhole. What are your thoughts on the James Webb Telescope's recent discovery at the edge of the universe?